Okay. So actually, I'm lucky that I had Jack and Yoshi talking before me. So a lot of the stuff I'll talk about, you've already seen some of the equations and things like that. And I should start by doing something similar to what Yoshi did, is make an apology, because in looking at what I needed to talk about, in looking at the different possibilities, I decided to talk about mainly things that I discussed in the symposium or the conference in late September, October. And so so I decided, though, most of the people here weren't at that. There was a few, right. The people that were, I figured this 2 months ago, and a lot of them forgot about it. And so it means that I only have to apologize to the people that remember what I talked about. So, and that's right. So anyway, so I'll talk about some more on stratified turbulence and some work I've done with Steve DeBreinkoff, and Eric has been involved, and actually there's even some ideas from Craig Winters in here. And so it's turbulence in stably stratified environments, and everybody has seen stuff like this. And in fact, here's a picture that a lot of people have seen in Drazen and Reed's book, and from a place near where Jack Herring lives in Colorado. And that's probably a early morning boundary layer with an inversion and a shear layer there that shows some probably Kelvin-Helmholtz instabilities developing, and you can watch them go into turbulence. And the one other example I thought I'd show is an ocean example, one of the few that I've seen where people have done good visualizations in the ocean, by J.D. Woods, where some divers laid dye out and then just watched the flow develop and instabilities and turbulence form. And these look very similar. And I want to bring out some scales here. From one of these roll-ups to the next is a few meters, and so that's going to be an important scale in the talk then. So seen in the atmosphere and ocean, and there's a lot that's known about these Kelvin-Helmholtz and other similar types of instabilities. And that isn't actually what I want to talk about specifically, but I want to talk about the larger scale dynamics that lead to these instabilities. And so it's a little bit, if you think of Jim McWilliams' talk, it's kind of the right side of his domain of how the energy propagates down. And I'm going to be looking, if it's an ocean case, at the last few hundred meters or so. And the scale, as Yoshi pointed out, one of the important scales in this problem is the Azimuth scale. And I'll follow the ocean example just because it's easiest. And in that case, it tends to be around a meter or so most of the time. And it's important because motions at larger horizontal scales can't overturn. Motions at smaller horizontal scales can. So typically in the ocean it's around a meter, and I'm going to be talking about things up to several hundred meters. And you'll see that in some of the data. I'll give an example of an atmospheric boundary layer where the Azimuth scale also is about a meter, and then I'll be talking about similar scale range up to several hundred meters. I think in the upper troposphere into the stratosphere, it's not quite as clear of the scales because I haven't seen good data on dissipation rates, but I think it's maybe, we're talking about scales from tens of meters up into the kilometer range, probably. So I'm interested in the motion on those scales, which then lead to these Kelvin-Helmholtz instabilities and turbulence. It's kind of the idea. And so then the first thing to think about are what are the important parameters in this range. And there's a Reynolds number then, and I'll define it based upon, say, in the ocean, it would be velocities on the say 200, 300 meter scale. So this L sub h, the horizontal length would be a couple hundred meters, and then the kinematic viscosity. So I have a Reynolds number. I also have a Froude number coming in that everybody has seen. And a gradient Richardson number is useful to think about because it'll tell us whether flows are stable or not. And that'll come up. And then the Rossby number as well. So those have been discussed a lot. And so now what parameter regime are we in these scales? Well, it's easy to show that the ratio of the Azimuth scale, so this is maybe a meter or so, to this horizontal scale of a couple hundred meters, that's to the 2/3 power at least is proportional to the Froude number. And so that's going to be a small number. So we're in the kind of a low Froude number range or a stratification dominated range, but if you estimate the Reynolds number, it's pretty high. So we're in kind of low Froude number, high Reynolds number regime. We expect internal gravity waves, but also, as you've seen in some of the simulations already, some quasi-horizontal motions. The gravity waves are thought to be a main source of three-dimensional turbulence, and that's what you hear most oceanographers talk about. But I think that these quasi-horizontal motions may be important as well, and I think you especially see that from Jim's talk. And then I'm going to assume that rotational effects are not important in what I'll talk about. And this is the regime that Doug Lilly called stratified turbulence. So anyway, what I'm going to do is describe what I mean by stratified turbulence, both in some lab results and some theoretical arguments, show some simulation results similar to what you've seen, some scaling arguments that come out of that, some similar to what you've seen as well, and then show some field data, and then try to draw some conclusions from that. So that's what I want to do. And in the lab, there's been some very nice experiments that have been carried out from a number of places at Flow Research in USC, Toulouse, Grenoble, Eindhoven. Usually in those cases, what happens is that three-dimensional turbulence is generated by a grid or by a sphere or something that's being towed through a tank of usually water that's with salt in it, and salt is used as a stratification medium. And as the grid is towed through, the Froude number is large and the Reynolds number is large and near the grid. But now those, it's kind of like an initial value problem, and those parameters decay. And as they decay, the Froude number becomes order 1, and you can show that that'll happen within a buoyancy period. And when that happens, the dynamics start changing significantly. Before that, they kind of look like normal turbulence, but then the dynamics change significantly, and these kind of quasi-horizontal motions develop, and you watch the flow, and you can see it undulating with internal waves as well. So both of these things are occurring, but generally in the lab, by the time this occurs, the Reynolds number is not very large. And in fact, the Richardson number, then, if you look at it locally, it is large. And so you watch these experiments, and usually you don't see kind of the classical three-dimensional turbulence occurring. Some of them, they're kind of right at the borderline where they do. So the scaling to geophysical turbulence is unclear, and I think some of it came about from the calculation that Jack just talked about. I'll bring that up again. So here's kind of a case of a very good experiment by Jeff Spedding at USC. And this is looking down on a case where he tows a sphere through this tank of water, and this is color-coded vertical vorticity. So it gives you an idea of what's happening in the wake. And you look at this, and you look at these vortices, and it kind of reminds you of a two-dimensional flow in a way. The scales grow and grow. And so you wonder, is that what's going to occur in the atmosphere or ocean?
The projection of stratification is vertical.
Yeah, so we're looking at the top, down from the top, it's vertical stratification, yeah.
So stratification is perpendicular to the...
That's right. We're just looking down at a tank of water, and they're using particle methods to measure vertical vorticity. Okay. And then they just color code it. But you can see the scale of these vortices just continue to grow in time. And then in the field, when you start looking at field data in these regions of on the 100+ meter scale, the Froude number is small. There you put a probe into the ocean, say, and you immediately see wave activity, which is the same as in the lab experiments. But often you see horizontally meandering motions as well. And talk to oceanographers that put buoys in and things like that, or you just watch on a stable day in the atmospheric boundary layer and watch a plume. They tend to meander. But in the ocean and atmosphere, usually you have three-dimensional intermittent turbulence occurring, which you don't see in the lab experiments. Now also, it's kind of an odd point to make, but these motions on the 200 meter plus scale are highly non-isotropic, so you don't expect overturning on those scales. And I only bring that up because a lot of the first interpretation of the field data in the ocean is that it must be isotropic inertial convective range turbulence, which it clearly can't be. So anyway, some scaling arguments are important, and you've seen this already. If you look at regions where the Richardson number is less than 1, where there might be instabilities, that leads to the fact that a buoyancy Reynolds number, which is the Froude number squared times the Reynolds number, has got to be greater than order 1. Oceanographers use this number a lot. And they find that from numerical simulations and field data and all that this has to be greater than something of the order of 10 or so to get three-dimensional turbulence instabilities and three-dimensional turbulence starting. So this is kind of a cartoon then of what parameter space looks like in stratified flows. And what I have here, these are logarithmic scales, and I have the Reynolds number that I defined here versus the Froude number. And so high Froude number is kind of normal turbulence. The stratification isn't going to affect things. So high Froude number, low Reynolds number, it's laminar. And then as I go up in Reynolds number, I get kind of the laboratory scale turbulence and then maybe geophysical scale turbulence at very high Reynolds numbers. Now when I come down into Froude number order 1 or less, which is the region that I'm interested in, then what I've done is I've drawn the line of where the buoyancy Reynolds number is a constant. So to the right of this line, I expect instabilities and turbulence, and to the left of it, I don't. And that's just a rough number. It's not meant to be exact. So the laboratory experiments, to a great extent, and most of the numerical simulations lie in this range here, whereas the ocean and atmosphere lie up here, where things are unstable. And so there's the question, do experiments down here relate to what's happening up there? So there's been some theoretical arguments that shed some light on this. First were Doug Lilly's, who argued that when the stratification is strong, the flow would be layered, and the layers would tend to become somewhat decoupled. If that's the case, then the vertical shearing of the horizontal motion would continually increase. That would lead to low Richardson numbers, and you'd expect instabilities to occur then. Now Biot and Chamaz brought up the zigzag instability and some related theoretical arguments to lead different arguments that leaded to kind of induced velocities and strong vertical inhomogeneities developing, and in particular pointed out the vertical scale of U prime over n, which Paul discussed a day or two ago. Now in the laboratory, where these flows are viscously dominated, this scale may not come in. It may never get a chance to come in because viscosity dominates it. Anyway, even though the Reynolds number is high, you can have a strong stable stratification. You would still expect small vertical scales to develop and local instabilities and three-dimensional turbulence. So you stratify it strongly, but if the Reynolds number is high enough, it's still going to be turbulent. And then there's a lot of questions about the dynamics of this when the Froude number is small and the Reynolds number is high. Does the energy go upscale or downscale even? And I think that simulation that Jack showed here was kind of enlightening because that made a big difference when the stratification went and you had three-dimensional effects coming in. And then there's questions about the effect on dissipation rates and things, and whether things scale up. So anyway, one way that we looked at this is numerical simulations, and you've seen some of those already with the Navier-Stokes equations and setting the Froude number small and the Reynolds number as large as possible to try to get into that range that I was talking about in the diagram. I'm going to show a couple of direct simulation results where it's time evolving, and then show a result where it's forced, and then some scaling analysis as well. And the time evolving flow, it starts out as a Taylor-Green flow, this strictly a horizontal flow, and we just let it develop on its own. We started out with an ambient density profile that's constant gradient, but no fluctuations and no ambient shear. So we just let this flow go, and we do it for different values of the Froude number and the Reynolds number. So it kind of looks like this. These are contour plots of a stream function at the initial condition and later in time. So the initial condition is Taylor-Green, so it's a cell type of flow, which has horizontal and vertical structure. Then as it evolves in time, this kind of shows part of the picture. You see scales growing to some extent in the horizontal and decreasing in some extent and the vertical. But so we analyzed these flows a lot, and one of the things of interest is just whether the flow stays stable. That relates to the mean square shear. And so so we take those calculations and we do horizontal averaging to get an idea of the magnitude of the mean square shear. And so this is the average of the vertical shearing of the horizontal velocity, the square of that, versus the vertical distance. And this is, for one case, it's kind of a moderate Reynolds number at a somewhat low crude number, and I'm showing 4 different times. Now this is a flow that's decaying in time, so it's an initial value problem, and it's decaying. It starts out with the peak value of this mean square shear of about 1/4, and then it takes off, and the shear starts to grow very rapidly, as both the Lilly's analysis and the Biant and Chaumat's analysis would suggest. By a time of 20 here, it's about 35 or 36 times its initial value, so it's grown very fast. And if I double the Reynolds number, actually it would be twice that. You can show this peak goes proportional to the Reynolds number. So
it's not normalized by the decay level, it's just absolute.
No, it's just absolute. So just this flow wants to shear. And so these concepts of shearing are really valid. So now to get a better idea of that, I look at the volume average Richardson number. So I take these mean square shears and just average them over the whole volume. And the average is about 9 or so initially. And in fact, if you look at the whole flow, the lowest Richardson number is over 3. So just if you use Miles' theorem, which doesn't apply here, it would tell you the whole flow is stable. But the fact is that this flow wants to shear out and become unstable. And so we let it go, and the shear develops strongly, and the Richardson number comes way down. And these are for 4 different Reynolds numbers. So if I follow this highest Reynolds number case, it's this one, the average, volume average Richardson number is down below 1 at this time of 15 or so. And so this flow is sheared strongly, and now it looks like it's unstable, at least in some regions. And so we go in, we look at the Richardson number on a point-wise basis, and in fact we find that a lot of regions of the flow are unstable, they're overturning and all. And this is just one example of kind of visualizing the flow. So the top plot is a horizontal cut through the flow of the vertical velocity. So it's just kind of a small piece of the flow. And when we look at that, we see, well, there's some oscillations along here. Maybe there is even some here. And so if we take this horizontal plot here and do a vertical cut along this line, kind of through these oscillations, what we get is this plot here. And this is now the density field. So it's going from heavy to light. And what we see is Kelvin-Helmholtz type of instabilities occurring, which is kind of what you would expect, because this flow starts shearing rapidly. Richardson number in various regions is well below 1, and instabilities occur. So the flow kind of has intermittent regions like this, which is not atypical of what you would see in stably stratified regions of the atmosphere and ocean. And we look at a lot of statistics, but this is one that has some useful information on it. And this is a horizontal spectra of the horizontal velocity, horizontal energy. And it starts out with this solid line here, which is the Taylor-Green mode plus some noise. And we let it evolve, and we see some energy going upscale actually here. But we see a very strong cascade downscale, which at least wouldn't be in the data I showed of Spedding's. And even though this flow is decaying rapidly, there's energy is transferred out to small scales fairly rapidly. In this time of 20, when it's kind of most energetic in terms of shearing, get this spectra here. And one thing we did notice is that it has roughly a -5/3 behavior. But yeah, thank you. Now Eric looked at this more carefully with some and found the following. So he was forcing turbulence with a subgrid scale model, and was looking specifically for these inertial type of ranges. And so he plotted a compensated spectra, and in fact found a decade or so of what looked like a nice spectral range, both in terms of kinetic energy and potential energy. And in fact, he suggests a constant of about 0.5. When we add that to our data, we find that his line roughly goes through our potential and kinetic energy as well. So even though there's significant differences in the calculations, they seem to have some similarities in terms of spectra. So you get down to this, there's some scaling arguments are suggested then. If you have strong stratification, Froude number is small, that implies there's a significant separation between the Azimuthov scale and the energy scale. So there's a significant separation here, which in fact makes it hard to simulate. Also, if the buoyancy Reynolds number is large enough, it implies there's a significant separation between the Kolmogorov scale and the Azimuthov scale. So there's separation here as well. Now, you can also argue that the dissipation rate in this problem should be independent of n, and in fact some data of Mike, Wade, and Peters shows that, as well as independent of Reynolds number, and some of our results show the same. And so you may have a range here where epsilon is the main parameter independent of n and nu. So, and this is in the horizontal. Now, if you argue that, you have a potential for an inertial cascade. So you have significant range of separation in these scales. The dissipation rate, actually the kinetic energy dissipation rate and the scalar, the potential energy dissipation rate are controlling parameters then, as well as K. And you wind up with power laws just like you would in Kolmogorov and Obakov and Corson's, but for very different reasons now. So you wind up with these, and in fact, you can suggest more things, like it may be that the horizontal dispersion would go as epsilon t cubed in this type of range. And it's a rationale also for why a vertical diffusivity that people use a lot goes like epsilon over n squared. And there's a nice paper in the other room about this. So this is what it suggests. And if it does, if this was right, it kind of replaces the idea of a buoyancy subrange. So, I was kind of dubious about this, and I'm still somewhat, but I start talking to oceanographers and find the following, that people are starting to see things like this. And so here's something that, first thing that made me more enthused about it was speaking with Jody Klimak, who had done some field measurements off the Hawaiian Ridge. They were towing an instrumentation chain, and so explain it as follows. These two are kind of cartoons to give the idea. So the first one are vertical spectra of shear, and this shear is k squared times energy. And the kind of what oceanographers feel is that, so to the right of this, it's k to the 1/3, which is consistent with k to the minus 5/3 energy. The minimum is about at the Azimuthov scale. And then the idea is here on this side that they're saturated waves, saturated internal waves. Now when you add Jody's data in, now we're combining vertical spectra, the light line, with dark line as a horizontal spectra. And there what we see is that this inertial range continues out, but it continues out to several hundred meters. So these are 10 to the 10 squared there. So he's seeing in the vertical, he sees things that follow the traditional idea in the vertical spectra, but the horizontal spectra goes much farther out. And so his real data, as opposed to his cartoon, look like this. So his strongest case, so the Azimuthov scale is here around 1, and this curve, he first was thinking about it just in terms of an inertial convective range out to like 300 meters. Well, that doesn't make sense as an inertial convective range, but it does make sense as a stratified turbulence range. So he saw it, then started to look around more, and Terry Ewart at the University of Washington Applied Physics Lab has a lot of data on a vehicle that self-propelled going through the ocean. And he had 15 sets of data that I looked at, and here's, and 12 of the sets look like this. The other 3 didn't. But he sees something similar down from about several hundred meters down to about a meter or so. There's a fairly nice 5/3 range in his data, and it's clearly not a convective subrange. So that set, there's another set that we found by Holbrook and Fair who used acoustic methods to measure vertical displacement, which is proportional to potential energy. And they claim seeing minus 5/3 in the open ocean, these blue squares, out to a kilometer or so. In the paper, again, they interpreted it as inertial subrange. And there's a set that just came out that Bouret, Overtot, Van Haren, and Pascal Lalonde have, which in a submarine canyon off the coast of Scotland, that they offer a similar interpretation. So there's that, and one other. So Rod Freelich at NCAR has been making measurements in very stable regions of the atmospheric boundary layer, and he claims he finds something very similar. This is frequency data, but he has essentially a constant 10 meter per second wind in the boundary layer, and so he can interpret it in terms of wave number. And his Azimuthov scale is right about here. He interprets everything to the right as kind of the Kolmogorov type of spectra, and everything to the left possibly in terms of stratified turbulence. So he has another set that's velocity data. The previous one was temperature data. And I think I'll just end with this one, so the possibility, there's possibility of the stratified turbulence if the Proud number is small and the Reynolds number is large. In the ocean, it might be from a few meters up into the hundreds of meters, and there's a strong tendency for vertical shearing of horizontal motion, leads to three-dimensional intermittency, three-dimensional turbulence with a downscale cascade, and there's this potential for an inertial region. So I think I'll stop with that.
So your dissipation, epsilon, is three-dimensional?
Yeah, it's very three-dimensional. Yeah, you can do a test of that. It isn't like totally isotropic, but it's close. Yeah.
I have a comment on that.
Oh,
I'm
yeah.
going to show tomorrow a data set which was taken through geoseismic data in the Gulf of Cadiz, and the minus 5/3 actually extends further than a few hundred meters.
Really? So is it the same methodology that Holbrook and Fair used? Do you know?
It's just a different experiment, but it's the same methodology and a different frequency of the source.
Right. Wow. Okay. Very good. Nice.
Any other comment or questions? So let's